मैं बस चेक कर रहा हूँ कि कैसे दिख रहा है यूट्यूब पे। या स्टार्ट नाउ। या इट इज देयर। रोहित, यू आर विजिबल ऑन यूट्यूब लाइव।
Okay.
मैं बस चेक कर रहा हूँ कि कैसे दिख रहा है यूट्यूब पे। या स्टार्ट नाउ। या इट इज देयर। रोहित, यू आर विजिबल ऑन यूट्यूब लाइव। आई विल शेयर द लिंक ऑल्सो ना। मैं बस चेक कर रहा हूँ कि या स्टार्ट नाउ। वॉइस थोड़ा बंद करता हूँ। Just wait few minutes.
We start in 2 minutes.
Okay.
क्या अब हम YouTube पे लाइव हैं।
Okay.
बाकी मैं सबको पार्टिसिपेंट्स को बोल देता हूँ कि ज्वाइन कर लें, है ना।
ठीक
तो
है।
एक बार आप बोल के देखो, मैं देखता हूँ कि वॉइस क्लियर आ रहा है नहीं आ रहा है यूट्यूब।
क्या मेरी आवाज आ रही है राहुल?
हाँ आ रही, एक मिनट, तुम्हारी आवाज़ तो वैसे आ रही है ना मुझे। मैं यूट्यूब पे जाके देखता हूँ इसको जैसे। हाँ, और यूट्यूब का लिंक भी शेयर कर दूँ।
ओके।
अब बोल के देखना कुछ।
एम आई ऑडिबल राहुल? क्या मेरी आवाज आ रही है?
We begin in 1 minute.
आवाज नहीं आ रही तुम्हारी।
मेरा आवाज आ रहा है? Can you hear me?
स्क्रीन शेयर करना जरा इस पे कोई।
मैं शेयर करूँ अपना स्क्रीन राहुल?
हाँ आ रही आ रही आ रही आ रही आ रही। यस, ये थोड़ा लैग लैग है ना, थोड़ा टाइम लैग। यस यस, आ रहा है। यार एवरीथिंग इज फाइन।
Great.
या ये एवरीथिंग इज फाइन, मैं शेयर कर देता हूँ।
मैंने किसी को एडमिट किया है।
फिर टाइम टू स्टार्ट।
Shall we begin, Rahul?
अभी आने दो ना, कोई आया नहीं है अभी ना, ज्वाइन नहीं किया किसी ने।
लेट्स वेट 5 more minutes or maybe
ठीक
10
है.
more minutes and then let's come back.
देयर इज अ वन पर्सन आई थिंक हियर, हेलन थॉमस।
हेलन थॉमस, सुमित, प्रांजल शर्मा.
अच्छा।
3 जन है ना? Yeah.
Let's wait a few more minutes. उसके बाद you can
Okay.
begin.
Yeah. We can wait 5 minutes. Yeah.
आपने एडमिट किया है क्या पार्टिसिपेंट्स को?
मैंने एक को एडमिट किया है.
हाँ ठीक है ठीक है, ओके। आप एडमिट मत करो, मैं ही एडमिट करूंगा, ठीक है ना।
Okay.
5 मिनट वेट देख लेते हैं, कोई और अभी आता हो तो ना, उसके बाद स्टार्ट करते हैं ना। 6।
ठीक है, कोई नहीं आया तो हम स्टार्ट कर देते हैं ना। वेटिंग रूम में एक एक पर्सन है, वेटिंग रूम में एडमिट कर। ठीक है, आप अभिषेक आप स्टार्ट कर दें ना, बाकी लोग आते रहेंगे अपने आप अपनी मर्जी से। मैं अपना ऑडियो ऑफ कर देता हूँ।
ठीक है, मैं एडमिट
लोगों को थोड़ा
Okay.
सा इंट्रोड्यूस करा दूं। वैसे तो कुछ लोग जानते हैं अभिषेक जी के बारे में। तो अभिषेक जो हैं, अभी फिलहाल में जापान में एक लिबरल आर्ट कॉलेज कॉलेज है, उसके अंदर ये मैं गलत हूं तो कहीं बताइएगा अभिषेक।
Yeah, sure.
मशीन लर्निंग और डाटा साइंस के ये प्रोफेसर हैं। और रोहित भी जो है फिजिक्स के प्रोफेसर, असिस्टेंट प्रोफेसर हैं। इंडिया में यूपी में एक जगह है, आई डोंट नो एग्जैक्ट नेम ऑफ द कॉलेज, मे बी रोहित विल टेल यू आफ्टर द सेशन।
इसका नाम है यूएनपीजी कॉलेज, उदित
जी
नारायण पीजी कॉलेज।
जी।
ये एक शहर में पडरौना, इट्स इन कुशीनगर डिस्ट्रिक्ट। हो सकता है
तो
कुशीनगर का नाम कुछ लोगों ने सुना हो। वैसे गोरखपुर का नाम सबने सुना है, गोरखपुर से करीब 80 किलोमीटर दूर है। वहाँ पे मैं हूँ असिस्टेंट प्रोफेसर।
और अभिषेक और रोहित दोनों ने मेरे साथ में ही हम लोगों ने साथ में ही पढ़ाई की है फ्रॉम यूनिवर्सिटी ऑफ दिल्ली से। अभिषेक का बैकग्राउंड बेसिकली ही इज इंजीनियर आल्सो, कंप्यूटर इंजीनियर। और आफ्टर दैट ही completed his PhD from Jamia Millia Islamia with the collaboration of IUCA in gravitational wave, if I'm not wrong.
Yes, that is correct.
Yeah, presently he is working on some machine learning and AI and all these kind of the things. So Abhishek, अब आप start करें. Thank you.
Yeah, yeah. So the mode of communication will be English. Yeah, हिंदी में मुझे चलेगा कैसे भी.
I think English is okay, fine.
English is okay. Yeah, yeah. Okay, great. Thank you for having me, Rahul.
Yeah.
And thank you for all the participants coming here. So I will give a short introduction. Actually, I was always interested in physics, but my graduation is actually in computers. I studied computer engineering. Then I was motivated to study general relativity. Then I ended up doing masters in physics from Delhi University and a PhD degree from Jamia Millia. And also I collaborated with the people in IUCA, Pune. So during my PhD, I worked on LIGO data, that is laser interferometric gravitational wave observatory. Okay, and right now I am a lecturer of data science in International College of Liberal Arts, Yamanashi Gakuin University. So this is in the Yamanashi Prefecture in Japan. And when I'm not working, I like to read philosophy and I love hiking. Okay, so what are we going to see today? So we are going to discover that using machine learning, we can actually rediscover Kepler laws. Okay, so that's the main goal of today. Okay, so let me give you a brief background of the story. We have all studied this. I mean, if you have a physics background, then you have studied about, you have known about Kepler and Newton. So Kepler almost spent, this is 9 + 5 years, but actually more than that. Okay, so he spent 20 years, roughly 20 years, just studying Mars. Okay, and there were other planets also that he studied. So he worked on this problem, which he compiled as a three laws. Okay, so he worked on this problem for 40 years roughly. And later on, Newton actually used calculus to prove this theory. Okay, so Kepler, when he took data, okay, he tried circles, he tried ovals. Okay, uh, he embedded shapes within shapes actually, and they did not fit the data. Okay, finally he discovered ellipse. Okay, so this is what we are going to demonstrate. Actually, I'm going to demonstrate you. Okay, so we will assume no physics. Okay, we will assume no physics, and I will just use the positions and velocity data from NASA Horizon spacecraft. Okay, which is in the next slide actually. Okay, let's go to next slide. So here the data set that you download. So this is for the planet Mars. Okay, so this is for Mars. So the data set basically looks like this. So on every day, okay, so this is daily observation of a planet. So X, Y, Z are the positions, okay. So this is a three-dimensional object, okay. So the planets are three-dimensional object, and the center is Sun. It is a heliocentric frame of reference, and Vx, Vy, Vz are the velocity in x, y, and z directions, okay. And r and v are basically the norm of the distance, okay, the distance and the velocity, okay. So basically r is equal to your r will be equal to square root of vx square plus vy square plus vz square, okay. So and similarly, sorry, so my bad. So this is I wrote this for this is V, okay. Similarly, you can write for R also, okay. And this is a cartoon, actually, where I have generated these plots. All the plots that you are going to see here are generated using Python, actually. I have not taken any plots from internet, okay. I'll talk more about the plot. I will demonstrate them in front of you. Okay. So let's do the first thing that we want to do is explore the data. So let's do the exploratory data analysis. Okay. This is a very essential step before you do any prediction. Okay. Later on, we will apply regression to accurately predict the orbit of Mars. Okay. So let's see how this data looks like. So if you plot the distance, so which is r actually, okay. So here r over a period of time. So this is time, your time, okay. This is also time. The day axis is also time, okay. The day column is also represents time only, okay. So you see this. So I will wait for here and see what patterns do you see? Or what do you see here? What story does it tell you? Okay. I'll just wait here. So here you can see X, Y, Z both. Okay, so you can see the legend here. All right, so you see X, Y, Z, and you have oscillations in X and Y, but not that much in Z. So what do you understand from this? So X and Y is oscillating smoothly. Z is nearly flat. There is a small oscillation, okay, but that is we can actually neglect. So what do you understand from this? This is my question to you. Anyone? Anyone? Orbit is in plane. Yes, orbit is in plane because there is no motion in the z direction. That's great. Okay. So this is something that is going to help us later. Okay. So z is negligible. There is hardly any motion. And this is true for any other planet. So in the code, when I demonstrate the code, we can change this planet to some other planet. Okay. And we can see the same pattern. Similarly, if you can see r here, so here r is basically the distance, the norm of the distance vector actually. So that is the distance from the sun. What do you see here? Here also you see oscillations, okay? That's evident actually. If you see oscillation in x, y, z, I mean, not z here, x and y, so you will see oscillations in r also. So what does it mean here? This, anyone want to try? And there is, so this is actually the maximum distance, okay, whatever the value is here, we can compute that number, okay, and this is the minimum value, okay. So the value is oscillating between two points. And by the way, I should have mentioned here the units, that is important actually, okay. So here the distant units are in AU, that is astronomical unit, okay, and the velocity and the time unit is actually is in days. Okay, so the velocity will be AU per day. Okay, the speed unit will be astronomical unit per day. Is this okay, everyone?
Yeah, I'm sorry. Actually,
Yes.
the setting was not that persons cannot unmute themselves. Now they can
Okay.
unmute themselves. If anyone has
Okay,
question,
that's great.
they
Okay,
can ask.
yes, it's good actually. I mean, this will be interactive actually. I will appreciate it. Okay. Okay, so now, any question till now? Maybe you can comment. What does it mean? when r, you see some oscillations in r, that is the distance. Okay, so you see the distance is not same. Okay, it is changing, it is varying. So that means definitely circle is not the orbit. Do you understand the logic? Definitely circle is not the logic. Okay, is not the orbit.
So
And
can you say that
yes,
the orbit is not closing into itself?
no, this is not the orbit where we will do plot the orbit. This is basically what I'm plotting is the distance from the sun. Okay, and that is going up and down. And that is basically bounded between two numbers, you can see.
Okay.
Okay, this is bounded between two numbers.
Oh,
Does it make sense? Yeah. So from here you can see this is actually orbit. This is actually a closed orbit, and this is a gravitational force. Gravity is attractive, so this is a closed orbit. And also you can see one more thing. If you see the x-axis is there is something in the chat. X and Y are also out of phase. Yes, X and Y are also out of phase. Yeah. But that's fine actually, isn't it? Anyway, we'll talk about that also. Okay, so here let me say this. So what is the distance between? So whatever the distance between this, it will be the time period of the planet. Does it make sense? It will be the time period of the planet. So roughly it is, and we are going to reduce this actually, this number. Okay, so it takes almost that much days to for the planet to go to a farther point uh, from the sun. Does it make sense?
the time interval between two apogees or perigees.
Yeah, so perihelion point and aphelion point. Okay. Yeah, I'm going to introduce these terminologies actually when we go to plot. Thank you for pointing it out actually. Okay, so yeah, so perihelion and aphelion, what are the definitions anyway? Since you pointed out, Rohit.
Are you
Maybe
asking?
we can go to. I have a plot actually. We can go to that, and we will discover perihelion and aphelion. Okay, so let's go to next EDA plot. Okay, which is speed and distance. So we have velocity and distance. What do you see from here actually? So when the distance is more, the speed is less. Okay, there is an inverse relationship, isn't it? So if a planet is closer to the sun, it will, so if it is closer to the sun, its speed is fast. Okay, so it will move faster compared to when it is farther away from the sun. Okay, and it is inversely proportional. Okay, so and same is true for other planets also, you see. So here you see some weird thing, like in Neptune, you see some weird things like oscillations. And mainly we can take these four planets actually. Okay, so I will talk about this, why that oscillations are there. It has to do with the amount of data we have. Okay, so Neptune takes roughly 165 years to make one orbit. Okay, Jupiter takes roughly 12 years. Okay, and I have taken data of 4 years only. Okay, so I have taken data of 4 years. So here, so if we have enough data, we can actually get the same pattern for other planets also. Okay, and towards the end, I have a task for you guys. Okay, maybe we can discuss that. Okay, let's hold that. So this pattern, that is inverse relationship between speed and distance that you see in all the planets. Okay, this is basically a character. These are all basically characteristic of central force. Okay, so let's see when you try to plot now. Okay, So here on, so now we have established that Z axis we can neglect, okay? The Z column we can neglect. And when you plot X and Y, okay, here you see the blue one is the actual circle. Okay, if you try to plot circle, so you don't get a proper fit. And the black one is the actual orbit, the data. Okay, see, let's take a step back and let me introduce you to Jupyter Notebook, okay, that I've made for this demonstration. Okay, so there we can see the plots, we can see the legend slightly bigger. Okay, so please bear with me 1 minute. Okay, here is a script. Okay, so that takes data. Okay, goes and takes data. So this will be available actually. So you can go to this NASA Horizon website, and you can download the data. Okay, you can download data, or you can write a small script. Okay, this is not the main theme. Okay, so once you have the data, okay, then we can actually, I want to demonstrate this. Okay, so here is the code. And there are some basic utility functions that you have. And let's, so these are some functions. Okay, so let's say we are working with Mars. Okay, so when you read this, okay, the Mars, if Mars is a string, okay, so if you read Mars as a planet, I've written a function that will basically get everything inside a data frame. Okay, so this is the data frame, and you can change this string to any other string, and you will get you'll get data frame of that planet. All right. Here you have the same plots which we already discussed, so I can skip these plots. Okay, so these are all produced in a Jupyter Notebook and Python. Okay, so here we have discussed this plot also. Okay, so here is the plot. So I want you to see the legend here. Okay, so the actual orbit is the black one, and the circular approximation, if you take this, okay, which is the mean value, okay, of the distance, okay, then it will be it does not fit well. Okay, and here sun is at the center, actually.
Hello.
Okay,
Hello.
yes, hello.
Uh,
Hello,
Sorry
yes,
to disturb you.
Ashish, yeah,
I have a question regarding
sure.
fitting method. Which fitting method you are using here?
I have not fit anything actually. I have just plotted the data. Okay. See, I have not done any regression. We'll go to it actually. Okay. So here what I've done, here I'm just plotting the data. All right, Ashish. Okay. And here I am plotting a circle basically. Can you see this?
Yes, yes.
Ashish? Yes. So
Yes.
I'm not, I haven't done any analysis right now. We are just doing exploratory data analysis. And here we see in the exploratory data analysis, we see that the circle is not a good fit. This is what we want to first be on the same page. That circle is definitely not a good fit. Okay. Is it okay?
Yes.
Yeah. So let me go back here. Circle is not a good fit, and perihelion is actually the closest distance, okay, which is the red dot, okay, and aphelion is the green dot, which is the farthest distance, okay, and we can compute. So we have actually computed this, and I can just show what is the perihelion and aphelion. Just maybe I can, just for the sake of, okay, it is this number. All right. So let's go further. Okay, so now we know that circle is not a good fit. Let's start talking about the first law. And so the first law is that the orbit of a planet is an ellipse. Okay, and we are going to find that particular ellipse. We are going to fit a particular ellipse and find the parameters of that ellipse. Now we are going to fit. Okay. So this is what we are going to achieve, okay? And let's see how we do this to answer your question, okay? So we start with the polar equation of the ellipse, okay, which is R is equal to, I mean, this is polar equation not for ellipse, this is for circle also. For circle, its centricity will be 0, okay, and P will be equal to R, isn't it? So we start with this polar equation of the circle, and we convert this, we cast this into this format, basically take the inverse of this, okay? So then now this is our regression line, okay? So our feature is cos theta, okay? So this is basically, you can say this is y is equal to mx. So this will be c plus m into x. Does it make sense? So x is our feature cos theta, okay? If you have done regression, so you might have come across fitting how to fit a straight line, okay? So this is actually, you see, cos theta, by having cos theta, you this is a transcendental a function, okay? So you cannot have a straight line. I mean, if you plot these things, definitely we have, if you plot these things, you have a circle. So you might be asking, where is the straight line actually, okay? So the straight line is, you have to cast it into this equation. Then you can see the straight line. And you have to assume that the feature is cos theta. Do you understand the setup, everyone? So now the idea is to find the best line that fits the data, okay? Okay, basically best fits the data means we have to basically find the value of m and c. That's the task now, okay? So let's go and see this. So these things, let me demonstrate here. Okay, it is here. Fit the, so theta perihelion, okay? So maybe before that, I want to show you a couple of things because so that we are on the same page, okay? So this is, I'm also using SymPy, okay? SymPy is a package in Python where you can write things in symbolically, okay? And here I'm using NumPy and Pandas, and here I'm using SymPy, okay, just to represent as a symbolic equation. So here you see, if we have a function which is this, okay, which is basically p divided by e cos theta plus 1, okay, that's a function we are working with. So for theta is equal to 0, if I put theta is equal to 0, I will get this exactly, okay? So I urge you to play with these actually. And we can change any value of theta, we can substitute. So this is a symbolic equation, okay? We can substitute. This is all Python only, SymPy I'm using, okay? So I'm basically, I should have said this. This is a SymPy package of Python, okay? This is heavily used in particularly physics, actually. So when you do theta is equal to 0, you get R min is this and R max is this. And if you solve this, okay, if you, we can determine E and P, basically just using this equation, okay? So this line, I'm basically solving for both E and P, okay? So, and this can be, this I'm sure you guys might have done using on pen and paper, and my focus is not on how to derive this, okay? Because I don't want to go into physics part of this, which you have done actually, okay? You might be familiar. I want to show you how to see this from a machine learning point of view, actually. So once we have E and P, so we essentially have the parameters, okay? And let's go here. So what are we training on? So we are training on this. So this is our train DF, okay? So our features are cos theta as we discussed, okay? And by the way, training size is 80% of the total data set, okay? And Y is, the target is 1 by R as we discussed, okay? So here you can see. And we do a linear regression, okay? Although this can be done from scratch, but I used scikit-learn, okay? So once you do that, so we can get a P fitted and E fitted actually, okay? P fit and E fit. All right, so this is plain from data. And here, if you have these R min and R max you can obtain. Okay, so these are two different ways to find. Okay, so this is if you have an orbit known, okay, if you have a complete orbit, then you can use just by using R min and R max, you can find E and P. But if you want to use machine learning, okay, you have to basically do regression on this line. Is it okay? So now when we use these parameters, okay, and try to plot, then we get the exact plot. Then we get the exact plot. So here I have actually shifted the sun to one of the focus. So the sun is at one of the focus and the other orange point is another focus actually. Okay. If the distance between these two focus is more, then the eccentricity is more. This figure actually still looks like a circle. Okay. From just from plain eye, it looks like a circle, but it is not exactly circle because the center is here. Okay. I mean, we already established that this is not a circle in previous plot.
Yes,
So here, yeah,
if
sure,
it were
sure.
a
Stop
circle,
me. Yeah.
sorry, Abhishek, for so if it
Oh,
were a circle, it would have they would have exactly superimposed on top of each other. So it's an ellipse with extremely low eccentricity.
exactly. Yeah, yeah. The eccentricity is this actually, you see.
Yes.
It is less than 0.1.
Oh yes.
This is you get, okay. So what you should understand, so the details you can actually see, uh, I mean, you can spend time and know the detail, but here is a regression, okay. I want you to know that regression is basically fitting a straight line. This does not look like a straight line, this because this is the ellipse, okay. Okay, I mean, uh, we are moving ahead of ourselves. We have to find that this is an ellipse, okay. This is not a circle. So we cast this into this equation, which looks like a straight line actually. So now we can apply linear regression. So that's the takeaway. Is it okay, everyone? And one more, I mean, in the plot, these plots are not straightforward actually. I mean, particularly the line joining the perihelion and aphelion. Okay, so these are not straightforward. I mean, you need to know, you need to find the direction vector actually. Okay, so this is a concept from linear algebra that I'm using here. Okay, so you need to find, we can go over it maybe later. Okay, so basically, and that line should pass through. If you join these two line, that line will pass through the focus. Does it make sense? Can I move further? Can I move ahead? Can we go to second law? So first law, what we learned, okay, I mean, you might know already, okay, what we demonstrated this is the orbit is actually a ellipse. Okay, so let me demonstrate this with a different planet actually. So at this stage, before going to the second law, okay, we can do, let me change here to say some other planet. Oops, I have it here. Any question from here, particularly the regression part?
Not the regression part. I have
Yeah,
a.
sure.
So, can you show us an example where the eccentricity is just too high?
It's too high. I think let's take Mercury. Okay,
Because
let me just
my
Mercury.
reason for asking this is because
Yes,
it's
yes.
regression fit, and if the slopes around the edges are too high, then that's where regression most likely breaks down. So, just to see how well this works, maybe a skewed orbit might show us better insights.
Well, all the orbits, if you take any, I'm not sure how much, I don't remember how much is the eccentricity of Mercury. Okay, it is the closest planet, and there have been studies of perihelion motion of
No, I
Mercury,
mean,
okay?
okay. I mean,
Yeah,
I
yeah.
want to see some orbit where it is least looking like circle. It should be too. Well, it's obviously too elliptical. I mean, I'm interested in that case if it's available.
Yeah, see, I'm using data. Let's find out whether Mercury uh, will offer us that you want to see. Okay, I'm just running this again.
Something like Uranus or Pluto. Might help.
Pluto is not in the list of planet actually.
Uh,
Okay.
yeah, I mean
Yeah, yeah,
Saturn,
yeah.
Uranus.
No, there's a good question you're asking because you see, I have 4 years of data. All right. Yeah, I think here we will see something. This is, by the way, Mercury. Okay, this is not Mars. Let's run this cell. What do we see? Still, it looks like a. Did I run this? Let me run this actually. Yeah, you see the eccentricity is not. I mean, it is changed now. Okay, it is 0.2, but still, for a dramatic. Um, it doesn't give a dramatic change actually. Okay, so here let me zoom out a little bit. Is this good enough as a demonstration for you? I mean, for me, it still looks like almost a circle actually. Okay.
Yeah. That's what I
Yeah,
meant.
yeah,
Visually, I mean, of course, it is eccentric. Visually, it's
yeah.
close to circle. So I was hoping that if there is some data here that will really
No,
visually looks like a very flat kind of a flat ellipse kind of a thing.
see, that is the thing actually. We can. I would urge you to create a fake data. Okay, create a fake planet, or maybe use data of Kuiper objects.
Mm-hmm.
Okay, I mean the particularly those satellites in the Kuiper belt. Okay, because those have actually highly elliptical orbits. Okay, so maybe any comet you can take. So those we will have. These are all planet data actually. So they are almost. They will. I mean, to naked eye, they will look like a circle.
Yeah. Okay. Understood.
Okay. Yeah. Yeah. Okay. And mm, yeah, we can go further actually. And at this point, actually, I will change this again, but this was just to demonstrate Mercury because I want to just work with Mars because all my demonstrations are on Mars. Okay, you see this for Mercury. You see what do you see from this plot? Actually, this is for Mercury. Can you see my plot? Can you see the plot here? If this is planet is Mercury, you can play with this. Okay, you can change the planets. If the planet is Mercury, you have that many oscillations, so many oscillations. That means what? And here, if you go, if you just compare Mercury with the same plot, okay, but this is for Mars, okay? Anyone? So that many oscillations, so that many times it has revolved around the sun. Does it make sense? Is it okay? So Mercury has, so clearly Mercury has a time period far smaller than Mars. That is what you see. What do you mean by this oscillation? So this is the highest point, okay? So this is the farthest point from a planet. So it has gone to 1, 2, 3, 4, 5, 6, that many times. It has gone to farther point. Is it okay, everyone? So let me run this again. Uh, because I want to use Mars only. Okay, so let's go to next. So uh, second law is basically the equal time in so equal area in equal time. Okay, so here so that has a consequence actually. So if you so this is same as saying equal area and equal time is same as a conserved quantity, which is angular momentum, okay? And you have seen this derivation, why this is true actually. If not, then we can do after the talk actually, because I want to demonstrate this quantity, basically plot this quantity, okay? And basically compute the area, all right? So let me directly show you the answer, okay? The demonstration first. So here, so what do you understand from this? So if you take a time window, okay, of 50 days, okay, here the blue one and the red one, both are 50 days time, okay, and these two areas are same. This is the demonstration, and this you can do in Python actually, okay. So how did we do this actually? So let's go. Let me actually go here actually. So let's say I'm not going to do the entire derivation. If you need, then we can actually discuss those things. Okay, here is your planet, okay, R1 distance, okay. So on time T1, it is at this distance, and next day, because the delta T is actually 1 day, okay. Every day you have observation. So next day, suppose the planet is here, and this is R2, okay. The area is actually so small area is this small area, okay. Basically this entire small area will be 1/2 R1 cross R2, and we can take basically this is the quantity I'm computing, and these are vectors, okay. Area is a vector quantity. Does it make sense? Have you come across this? Anyone? If not, then I can explain further. This is what I'm going to compute actually. So basically we take cross product of these two quantities, okay, cross product of these two quantities, and then when you do cross product, then we can let me actually go here extra, okay. Oops. So what is R1, R2? These are vectors actually, and these are you can write xi, j, okay, plus zk, okay. So you can have these. I want to open this notebook because I have some symbolic computations here, okay. So once you do this, which I'm going to shortly show you actually. So we can arrive at R cross V, okay. R cross V, okay. So I'm actually missing out a couple of things. I should not skip, okay, everything. So R1 is this, and R2 is, we can say R2 will be equal to, okay, say in next day. So suppose the speed of the planet is going with speed v, and delta t, okay. So delta t is 1 actually here in this case. So here R2 will be R1 plus, if you see the figure, okay, R2 will be R1 plus v delta t, okay. Does it make sense? R1 plus v dt, okay. So when you do R1 cross R2, okay, so R2 will be, so R1 plus R1 cross R1 will be 0, and it will be, so this quantity will be basically R1 cross v dt, okay. So this is dA, okay? Then you can have dA by dt is equal to this thing. Okay, so basically it is the cross product of r1 and the velocity vector.
Yeah. Sorry, there is a question in the chat.
Yes.
The
Yeah,
someone
I
is
did not see.
asking,
Can you read
yeah,
the question?
where is this data taken from? Where is the data taken from?
I said that the data is from the Horizons, NASA Horizon satellite. You can go to this website, okay? I have used the API directly, so maybe we can go here. Okay, let's go to Horizon Systems app. Okay, so either you can do manually, so here, or you can write a code. Okay, so when you do this, so target body is Mars. Okay, so this is where you will get the data. Okay, all these data. Okay, so right now I'm actually focused only on these columns only. Rahul, is it fine? So what I've done is basically I've automated this task actually. Okay, so you don't have to go and download download data for all the planets. Instead, you can just use this and get all the planets for this start and end date. Is it okay? Okay. Here, here what I wanted to show you here is oops, it is here actually. Yeah. So second law. Okay. So here I want to show you if you do R cross V. Let me zoom in here. If you do R cross V, okay, and if you do R cross V, yeah, you will get a quantity. Okay, so let's do this. Let's run this. If you when you compute R cross V, everybody is with me. Why we are computing R cross V? Because we want to find the area, and that area is also related to the angular momentum. Okay, is it fine, Rohit? So when you do this,
it is fine. It is fine.
it is fine. Yeah. So when you do this R cross V, okay, I'm using again symbolic. This data structure is symbolic, SymPy. Okay. So when you do this, you get a vector R cross V. It's a cross product. Okay, you get a vector. But then we substitute VZ and RZ. Okay, so that is basically the we know that there is no motion in the Z direction. So that is why I mean negligible motion. So when you do this, you get this quantity. Okay, so these is 0. Okay, and you get this quantity basically. And when you plot this quantity, basically I will be calling this as LZ. Okay, when you plot this quantity, okay, you get a figure like this. If you just look at it, then you will see that it is oscillating. It is not a constant. But when you see the y-axis, these numbers, this oscillations is very small. Are you with me? These oscillations are really very small. I mean, if you take, let me demonstrate this. The variation, see the variation is this much, which is a very small variation. You see, this is all 0.02113. Okay. The variation is very small. I mean, in the plot, it looks that it is varying, but it is actually constant. If you do this, so let me actually round this off. Okay, so let's round this off to say round this up to 4 decimal places. Okay, so this is actually a constant LZ. Okay. So what you saw earlier is basically a statistical fluctuation. Okay. And the error is systematic. Okay, now another demo I want to show you here. If you provide any start date, okay, so I've written a code here. So if you provide a start date and number of days, okay, say I want that many days, say 10 days, okay, 15 days, okay, so then you will know how many, what is the area of that particular sector. Okay, if you start from day number this, and if you go say 20 days from that, okay, so let's take 40, okay, 40 plus 20, so day number 40 to day number 60. Okay, if you do that, then that will be the area. Okay, and from 99 plus 99 plus 27, 99 to 99 plus 27, that will be the area. Okay, I've written the code. Actually, I can go over the code, but the demo is this. All right, so sun is at one focus, and when you do this, actually, so let's take this. This can be any arbitrary number. Okay, so this is coming out to be, so this is what is equal area in equal time. So this time is equal, okay, and the area will be equal. If you want to go quickly, we can actually go over the code, okay, or maybe we can go over the code later also. So here is the code, okay, so get area. So here I am doing basically R1 is there and R2 is there. I'm doing basically R1 cross R2. And I'm finding the norm because the R1 cross R2 is basically a vector, okay? You need to find the length of that vector, all right, to get the area here. So for that many days, by default, you compute for 1 days, okay? But if days is something different from 1, so you compute for that many days. You have a for loop actually going over that many days, all right? And then you accumulate the area, basically. You initialize area to 0, okay? So then you have some code to plot actually, okay? All right, so let's go further. Rahul, that question is addressed so from where the data is taken.
Yes. Maybe Sumit was asking. So,
Okay.
Sumit, is it okay?
Yeah. I asked it towards the beginning, so yeah, I got it.
Yeah, okay. You see, and while just for completeness, this is equal to this, okay? And by the way, I'm forgetting a factor of 1 by 2, okay? We have a factor of 1 by 2 here, all right? And a linear, angular momentum is actually R cross P, okay? And this is R cross P is what? P is, we write P for momentum, okay? So mv, and mass is mass of planet, okay? So this will be again R cross V. You have the same quantity here, so that is why you have this relationship. R cross V will be L upon, we can write 2m, okay? So that is how area is related to angular momentum. And just that we are doing this, okay? So dl by dt, if you take change in angular momentum, we can just take, let's drop let's drop m and 2, the constants. So let's take derivative of this quantity R cross V. Okay, if you do this, so this will be dr by dt cross V. Okay, remember all these are vectors, plus, can you tell me, R cross dv. This is simple derivation, so I just want to motivate you actually, okay? So this is actually dr by dt is actually v. So v cross v will be 0 because they are in the same direction. A cross b is equal to ab sine theta, okay? Sine 0 will be 0. So this is 0.
Can you hear me, Abhishek? There is one small.
Yes.
Sorry for interrupting so
Yeah,
abruptly.
yeah.
So shouldn't there be another factor here, m mass?
Yeah, mass, I'm just neglecting mass actually. Neglecting means you can put the mass will be here actually. So here will be mass, okay?
Okay, so
Mass of the planet will not change, so I just dropped it actually.
okay, my apologies. I
All right.
actually got distracted for 10 seconds for some work.
Yeah. The mass of the planet is definitely there. I just removed it, okay, for a short derivation. So, and what is this? This is basically your acceleration. And for central force, acceleration is in the same direction as the mm, r vector, okay, the radius vector. Okay, so this is basically the distance, and the acceleration will be towards the center, and the distance will be away. Okay. So in this case, the angle between these two will be 180 degree or pi. Okay, so that is why this will also be 0. Does it make sense? So that is why we say angular momentum is also conserved. Okay, so let's move further. Okay. So we basically plotted LZ, all right? And I demonstrated you this also.
Abhishek, you have 10 minutes left roughly.
Okay, so let me quickly do Kepler's third law here. Kepler's third law is we cannot prove this using one planet. We have to do with multiple planets. Okay, so here we need to prove that t square by a cube is a constant. Okay, so what we can do here, we can assume that we can assume that it is t square by a cube. Okay, so let's say we t to the power a, k to the power, it's okay. So let me take p and q. Okay, so we can assume this, and here we don't know p and q basically. Okay, so here let's take log on both sides. So p log t is equal to log k plus q log a. Okay, so once you do this, now maybe one more line I can do. I can divide by p. Okay, is it all right? So here, if you look, this is actually our straight line. This is y is equal to, this is again c plus this will be m, and this will be x. Does it make sense? So here we can do another regression here. Okay, and if you do regression, we the slope we will get as 1.503. The slope is this quantity, okay, q by p. If q by p is 1.5, then we can take q as 3 and p as 2, which is 1.5. Okay, so that is how we can actually prove or demonstrate the third law also. So third law, we can quickly see the third law also. Okay, the third law here. I'm sorry, there is a lag here. Yeah, we do for 4 planets only because, as I mentioned you earlier, a lot of data is required to do for other planets. For example, for Jupiter, 12 years, for Neptune, 165 years. Then you can see this quantity, which is t squared by a cube, that is throughout constant. All right. So here, this is what I wanted to demonstrate, Kepler's law. Let's go to the slide again. There are some extra things that I have here. Okay, so why not Jupiter and Neptune too? This I just explained. Okay, so because we need more data. And there are some extra things which I can skip here because we don't have that much time. Okay, so basically we can do a Fourier regression also. If we consider these as features, okay, then we can actually fit the orbit. Okay, we can do the same with linear regression if you consider these as features: sine theta, cos theta, sine 2 theta, and cos 2 theta. Okay, and you will get the perfect fit also. And here, this is just for fun. How these planets the orbits will look if you visualize from Earth. The blue dot is actually Earth. Okay, so Kepler was unable to explain this actually, and pre-Kepler people also were puzzled in astronomy. Okay, why the planet which is moving like this will go a retrograde? Okay, while it will, because we are viewing from Earth. Okay, so we can do a change of, so this plot was also not straightforward. We need a change of axis because right now we have data from Sun. We need to change the coordinate system. Here also you need some ideas from linear algebra. But you can see the code actually. Okay, so any question? Because I would like to stop here. These are the things that I have used for the demo actually. Okay, so a lot of ideas from linear algebra and programming concepts. Okay, so I've used Python. I've used particularly NumPy, Pandas, and SymPy also. Okay, and Matplotlib and Seaborn for plot. Okay, and we have done supervised machine learning. So I would like to stop here right now. So we just use a machine learning tool, and we rediscovered what was. I mean, Kepler took this over two decades. Okay, and Newton had to invent calculus, but we just use some regression. Okay, and we discovered the same laws.
I request to audience, please ask questions.
Sure.
I have a
Sure.
question. I have a question.
Yeah.
So this is first of all, this is great work. Okay, much appreciated.
Thank you.
I have a question. So you're saying that given a data and already knowing the law, by law I mean the mathematical formulation of the law, you can do exactly what you did and basically uh, know what the mathematical formula for the data representation, right? I mean, it's sort of like you already know the law and then you are verifying it with data, right?
But I did not use the law as the input anywhere. You see. See,
I
we
think, okay. Yeah, please go on, go on.
no, I did not use that as an input. I mean, you see, from the exploratory data analysis and the plots that you see here. Okay, so this is actually telling us that it is not a circle.
No, but
Okay, I just plotted here.
why was I expecting it to be a circle? I mean, no, nothing
Yeah,
tells me it should have
yeah,
been a circle, right?
because circle is easy actually. I mean,
No. Again, I mean,
we
then
start from circle. Yeah.
yeah, but then I'm already biased, right? I'm already hoping it to be a circle, and then find, oh, it's not a circle. But
Yeah.
why did I expect it to be a circle? It could be some random shape, right?
Yeah, it could be random shape. I mean, it's an orbit actually. It is a bound orbit. Okay.
Correct. How do
So
I
the
know?
simplest thing that no
Yeah,
wait,
one.
wait, the simplest thing that I can assume is a circle, but then we found out that it is not a circle.
No,
Does it
but
make sense?
the moment you assume it's a bound orbit, you already assume you know something about the system.
Yeah, it is central forces actually. Yeah.
Yeah, if you know it's a central force, then I already know Kepler's law. So
I'm not.
I'm going into a data analysis assuming I'll already know something about the law. Although
No,
it's
I'm
not
not
a direct
assuming.
input in the analysis. I mean, no. So I'm saying
Okay.
today if I do some experiment in my home and I just give you the data and I tell you absolutely nothing about the system, would we be able to discover a mathematical formulation for that data? I tell you
Yeah,
absolutely
sure.
nothing. Yeah,
We
because
can actually. In
yeah.
fact, what I will urge you is do this task, okay? So this is actually speed versus distance, okay?
Yeah.
So let me go here. So speed versus distance, I just mentioned that it is, see, at first it will look unrelated, but please hold, okay? Please understand this. So this is a inverse relationship between speed and distance, okay? And this is one planet only. If you do this for every planet, you will have some kind of, okay, but the shape will not be exactly this, okay? So I want you to deduce whether this is equal to 1 by r or not. I mean, not 1 by r, it will be some constant. Okay, so we can deduce. So we can begin with some alpha and beta here. Okay, the way we did the third law, actually. Okay, and then we can find, let's take this law.
No,
Basically, this is
but
exactly
how do
this.
you? No,
Yeah,
no. I have a quick question. So why
yeah.
should I start with V alpha proportional to 1 by R beta? Why not V alpha equals to log of R beta, or log of square root of cube root of R beta? How do you know that I have to start here?
Yeah. Okay. So because I want to demonstrate you some regression. Okay. And if you want to really have a the free functional form, the best way would be to go for neural networks actually.
That is what I was basically
Yeah.
assuming. Yeah,
Yeah.
because
If you really don't want to assume anything, but
yeah, that's how real world works. Right? I have a date. I have no clue the functional
no, no,
dependence.
no, 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 no. See, that is the thing for researchers that we should get neural networks is like if you have that many parameters, basically by introducing neural networks, you are adding more dimensions, okay? But as a data scientist, or in this case, as a physicist, what information or what constraints you are giving, that is important, right? I mean,
Correct.
if you can take a neural network, but what will be the motivation? Here, the motivation is V is looks like inversely proportional to R. Let's and when you plot, okay, it looks like, so let's assume that it is circle, okay, because of Occam's razor also. See, these, by doing all these things, by doing these things, you are basically trying to find a simpler model, isn't it?
Yes, I mean, see, it basic from the curve fitting, right? So you are discovering the
Yeah,
values of parameters. You're not discovering the functional formulation of the data, right? You discover, so
yeah.
here
For
you discover alpha and beta. Here you're discovering the value of alpha and beta for this graph. But if this graph was some crazy looking shape, then we are stuck, right?
no, we are not stuck. I mean, that depends. See, if you do sales data, for example, sales data, or if you do in physics, actually the data are clean. All right. Physics, that even the time series data, if you take power out of time series data, the data will be clean. But if you do data in economics or say political science, here I'm working with people. Okay, so there the data is really bad. You have to
Yeah,
put
yeah.
lot of assumptions. Yeah, yeah,
Yeah,
yeah.
yeah.
So
So,
if
for
you
example,
have,
I was trying to look at it this way. So, for example, if I give you a pure position and time graph data for double pendulum, and
yeah.
I do not tell you that it's double pendulum data, can you
Hmm.
arrive at a conclusion using these techniques that it was actually a physical system with that looked like a double pendulum?
This
So
can be done actually. Yeah,
I
yeah.
give you,
This
yeah, I
can,
give you
yeah.
nothing
See,
else, just position time data,
yeah, yeah, yeah. Sure.
because it's a highly chaotic system. We all know.
Yeah, see, once you bring chaos, then you will not have any equations to
No,
describe
I
it.
don't know if it's chaotic. I mean, it looks chaotic, right? That's the whole point. I don't even know is it chaos or non-chaos. It is what? I mean, I just have a
No,
bunch of readings.
okay. I can share with you one work I did. So here, in cosmology, so we predict the Hubble parameter. Okay, so there is a Hubble parameter that is related to the expansion of the universe, and here, for simplicity, V is equal to hd. So as you move further, the velocity of the object or astrophysical object, the galaxies, will be fast. Okay, so they are going at a faster rate. So V is equal to hd. Let me write here. Okay, so here V is equal to hd. So this is the simple law, Hubble's law, we say. But here we can assume, actually, there are some words actually, and where they have not assumed this functional form.
Sorry to interject.
Okay.
If I'm eating away
Can I
time from
finish this?
another speaker, yeah. So no, just apologizing if I'm eating away other person's time. Yeah, feel free.
No. What I'm saying, we can actually take a neural network. Okay, so the problem with the neural network will be you need too much data. Okay, you can if you even if you have data. Okay, so if you have a constraint. Okay, so that will be like additional information. So as a data scientist or as a physicist, um, you would want some additional information. Does it make sense? So that is why it is desirable, actually. What you're saying is I don't know. Let's not assume the functional parameter, functional form, and we can do. Yes, you can do. It will take a lot of time, actually.
Yeah. Okay.
I
Yeah.
think, yeah, I would like to stop there. Yeah.
Thank
Let's
you.
take more questions. Yeah, sure. Yeah, any other question? Thank you for the question, actually. Yeah, but let's take more questions. I mean, this is the inspiration of PINs also, PINN, physics informed neural networks also. So
Maybe
there you have.
Mukesh ji is asking something. Yeah.
Yeah, sure.
Hi, Abhishek. This is Mukesh. Nice talk. And
Oh,
sorry,
hi.
I joined a bit late. So I have a question about so how to include this thing in classical mechanics subject. So, for example, I'm going to teach this semester the BTech first year, and they have this
मैं
Kleppner
आप
and
लोगों
other
को बता
things.
दूं,
So
एक मिनट में आपको बता दूं कि मुकेश जी he is an
Uh,
assistant professor in triple
I see.
IIT Vadodara.
yes, yeah.
That's great. Yeah, so the idea is to Python. Maybe I can ask you directly how much programming or Python you know, because this code base is in Python, actually.
Actually,
Actually,
the
this is a good question. This actually takes us to this slide, which is what my final slide is, actually. Okay, and I was thinking to talk about this at some point. So,
right. So yeah,
yeah.
Abhishek, yeah, sorry, yeah. So actually,
Sure.
the we are still in the classical model, right? Just the teach and lots of numerical and lots of big derivation, and sometimes the
Yeah.
student just like they lost and just they do the mathematics, but they didn't understand what is the physical significance and application, right? So I'm also going to teach the probability and statics. So how to combine this thing, like I'm an experimental physicist, okay? So that's one of the problem with me. But although like how to combine in the syllabus, so they have a bit, a small like the classical thing, and then we go to the application. Okay, here is the application, and we are in the AI era, right?
Yeah.
Artificial intelligence everywhere. So what is your suggestion and how to go step by step in this area?
Yeah, I mean, first you said experimental phases. Actually, for experimental phases, you have to know the theory also, and then the experiment part also. So experiment physicists have a lot of work to do than theorists, I would say. Actually, truly speaking, they need to know the theory also. And so to make things interesting, since you are a teacher also, it's a good idea to use programming. Yeah, Rohit.
Yes, continue. I had one small point or a question.
Yeah.
You can
Okay.
treat it whatever way you want this to. I think if you start with black body radiations data and
I did not answer his question.
can
Okay.
a
Anyway.
non-physicist discover Planck's constant? It's very hard to tell because you have to try lots and lots of permutations and combinations. You have to. So I think if one wants to rediscover, I repeat, rediscover, not discover, rediscover the Kepler's law, I think it can be done using machine learning, but it's going to take a while because he has to he has to manipulate the parameters in lots and lots of ways to finally come up with a
Yeah,
consistent picture.
the parameter space will be too huge, actually. There's
Rediscovering
a
Planck's constant would be even harder. I would
I
think.
mean, at that point, it's just statistical search, right? I mean, I give you a bunch of
see.
million things, and then you go through all of them and arrive at something. I mean, then it's just statistical searching.
Yeah, exactly. So where are we bringing the ideas of physics? Actually, we are not actually. If we are going in that direction, we need to constrain our approach, isn't it? So what is physics? I mean, in my understanding, actually, physics is a story. Actually, okay. If we see the story is If we don't find this story, okay, will does not match to the data, we will change the story actually. Tomorrow, if we see suddenly things are going up instead of falling down, we will change that story and we will find some other another explanation, isn't it? So physics, according to me, is a story, but that story confines us actually. This is my understanding actually. I mean, we can argue on this.
No, that's okay. I mean, that's a very different discussion. And thanks again for Rohit as well as Abhishek.
Yeah.
So, yeah.
I was talking about Mahesh ji. So Mahesh, I think we can talk about this more, and we are offering a course actually. So and we are particularly, this course is for people who are doing physics. Okay, so we will focus on not how to use the modules, Python modules, sklearn, or okay, or for example other modules, so various statistical modules, but the focus will be on the math behind it. Okay, so I will go over all these points. Okay, I will go over all these um, topics. Okay, so particularly say if you want to if I want to give a rough idea, programming is going to take, I have a note actually, so programming is going to take, I thought about this, is going to take 10 hours particular. Okay, linear algebra is going to take roughly, this is 10 hours, this is roughly 20 hours it is going to take. Okay, and calculus we don't need integral calculus. People doing physics, we already study too much. Okay, we just, for data science purposes, we just need derivative. Okay, and that is maximization, minimization, and also we need to know the Lagrange multiplier and optimization problems, because we will be working with constrained optimization problems also. Okay, to understand support vector machines. So I will do all these. So that's in the mind actually. So I will go through all the mathematics and I will demonstrate actually all these in Python. So that is why programming is very important. We will begin with programming. So you see, linear algebra, calculus, probability theory, and statistics. These are four pillars of any data science project. Okay, so we need to master this. Okay, and I think probability and statistics will take, these two will take 15 hours.
Hello.
Let's say 15 to 20 hours. Okay, and then, yes.
I want to ask you some topic related to physics informed neural networks. My whole work is going to be in this sector. I have nothing know much about neural networks, but I know I have some idea about input layer, hidden layers, and output layer.
Yeah,
So
yeah, yeah.
basically, I am also in the experimental part of physics, experimental nuclear physics. So in heavy ion reaction or any nuclear physics experimental uh, data, so how we can uh, implement this thing, neural networks? How can we implement neural networks in our real experimental data?
No, we will see how to, this is a very broad question. Okay, we employ these things on real data only. Okay, so basically I have to know the problem, so I have to ask you the problem actually. Okay, so in most cases actually, okay, if you're doing nuclear physics data, then you don't need a convolution neural network, you don't need, is it a time series data, may I ask you? I don't think it will be time series data also. You are studying some scattering cross section, so I think it will be a regression or classification problem, or it will be yeah, you have to draw, make some hidden layers, and you have to experiment with different hidden layers actually. I mean, this question itself is a broad question. How you will do means, uh, I mean, for that, you have to
Yes,
know
yes.
the problem actually.
Because in last year, we have to calculate only the cross section of different physical nuclei. So there is very huge amount of data we have, almost in your heavy active or other type of scattering is well, means
Yeah,
photon
yeah.
colliding or anti-platelet colliding. There are many types of reaction or scattering there. So my whole work is going to be neural networks. So,
Yeah. We can
so
talk more on this actually. Yeah. You have a background in machine learning. You have already, or programming. You
yeah,
have done.
I have know about code. I know about well-known giant force simulations and Python. This thing I know very well. But question is that how we can use neural networks on this I don't even understand it.
Yeah. I think I don't know your problem, but I think you can write a ANN or artificial neural network. You don't need to do a.
Artificial neural network. Yeah, you are getting
Yeah.
my
Yeah.
point.
So work with hidden layers and.
Ashish, your voice is very unclear actually.
Yeah, it is. No, it's fine, but the question is broad. We can talk on the data that you are actually working. You can contact me. Okay, you can write to me email.
Yeah, yeah, okay. Thank you.
Yeah, sure. Anyway, yeah. And these are the topics actually. Yeah, the natural language processing and generative AI. I am particularly interested actually, so I am doing it. So when I do these things, I read the research papers also. So the Google's paper attention is all you need. That is everybody will uh, ask you to read that paper. Yeah, that is good. And there are a couple of other papers also which one should go. And there are a lot of resources actually. So idea is to uh, accumulate and provide them in a coherent form. So that will be my main task actually. So behind the motivation behind this courses. Okay, so this will be one course, but right now these tentative topics these are not yet ready, but we can actually begin with programming, and depending on what the level of most students are, we can actually accomplish things in a higher pace, or I mean it depends actually. So any other question actually?
Yeah, I encourage the audience, please ask questions. We have already about to finish the session. So many people actually apply for the session, approximately 100, but very few joins. Maybe I don't know what is the reason. So Akansha, Helen, Sayan, anyone has any kind of question? कोई भी question है आपको तो please ask. Please ask. Abhishek is here.
Yeah, I'm here, and you can write to me also. That is not a problem. Okay.
So, Abhishek, currently you are where located in India or outside?
I'm here in Japan, actually. It's in Yamanashi Gakuin University. Yeah.
Okay. Yeah. Okay, I will also write you. So maybe we need some, lecture on either some machine learning or something. So yeah, I will keep in touch. I will take your email ID from Rahul Bhaiya.
Sure. Yeah.
Yes.
So everyone, please keep in mind that the Japanese time is 3.5 hours ahead. So if it's 2 p.m. right now in India, it must be what 5:30 in.
Yeah, exactly. It is about to be 5:23. Yeah,
Yeah.
exactly.
So Abhishek,
Yeah.
can
Three
you
and a half hours ahead.
the name of the prefecture that you are currently at? Is it Yamanashi, Yamaguchi,
Yamanashi.
Yamanashi? Okay.
Yeah.
So if
I'll
they
remember that.
Yama means mountain, actually.
Okay.
This is surrounded by mountain. Yeah.
So if there is no more questions from the audience, तो मैं एक ये बताते हुए कि हम लोग एक कोर्स एक शॉर्ट कोर्स स्टार्ट करने का प्लान कर रहे हैं एंड आई विल टेल ऑल अबाउट द कोर्स इन द व्हाट्सएप चैनल और वी ऑलरेडी है मैं उसमें बता दूंगा सबको जो भी व्हाट्सएप ग्रुप हैं व्हाट्सएप चैनल हैं हमारे और मे बी वी अनाउंस ऑन द यूट्यूब ऑल्सो अगर आप में से कोई भी या आपका कोई कलीग या कोई फ्रेंड कोई ज्वाइन करना चाहता है किसी की रिसर्च में ये कोर्स अगर हेल्पफुल हो सकता है तो बहुत अच्छा लगेगा हमें इट विल बी पेड कोर्स डेफिनेटली बट पे विल नॉट बी वेरी हाई जस्ट फॉर सिंसेरिटी और रेगुलरिटी के लिए एक नॉमिनल चार्ज वी विल अनाउंस सो ओके सो आई एम गोइंग टू एंड दिस मीटिंग एंड थैंक यू टू अभिषेक एंड Rohit as well as
Yeah, thank you.
yeah
Thank you, Rahul.
Thank you.
Thank you. Yeah.
Excellent discussion, Abhishek, Rohit. Excellent.
Yeah.
work.
Thank you, Sumit. Actually, thank you for bringing this up. Actually,
Sumit,
and
पहचाना लग रहा है. Sumit from Delhi University. मेरे बैच का चश्मा वाला.
Yeah. Yeah.
Okay.
oh, I see. Yeah, I think I know you. Yeah, Sumit.
Yeah,
I've
I
seen
know
you.
you guys as well.
Oh, I see. Okay. Yeah. So, what are you doing now? Maybe we can talk.
Yeah, we can
after
take it.
we
We can talk
finish
offline. Yeah.
offline. Yeah.
Okay.
I'd like to get in
Thank
touch
you
with
again. Yeah.
sometime.
We are going to end the session. Thank you to everyone. This is a very nice session. Thank you, audience and speaker as well as. Thank you.
Yeah. Thank you. Bye.